Welcome to Class 10. So you've now got, I hope, a pretty complete coverage of color science, color theory, from the front end to the back end of the whole chain of digital cinema and HD production, post-production, distribution. And today's class will serve as a bit of a wrap-up. The main topic will be logarithms and log coding. And I've mentioned log coding in several previous classes very loosely, but I'd like today to kind of underpin your understanding of log coding with a little bit of mathematical theory and then some practical implications with respect to how digital cinema and HD material is captured, particularly the exposure range and how light relates to the coding range. So we'll cover logarithms, and logarithms also turn out to be pretty important in the OpenEXR image coding, and that is definitely the way of the future for high-end production. And with an understanding of logarithms, we can go into a kind of deep conceptual diagram of bit depths, and I hope you'll get some good understanding of bit depths. So let's race through logarithms, and I should tell you that the slide rule that I'm using in this title slide is actually my own slide rule, and I know how to use it. When I went to university, let's just say in the 70s, a long time ago, when I started university, I used a slide rule for calculations in engineering school. And by the time I left university, well, that was many, many years later, I had a calculator. So understanding how a slide rule works is very intimately connected with how logarithms work. But another way to understand logarithms is to start with our everyday words that we use to describe units of time, or let's say intervals of time. And we use everyday words like second, minute, hour, day, month, year. But you find if you look at the time periods that are associated with these words, 160, 3,600, 86,000, this is the number of seconds in each of these words. And so you see that each new word is associated with going up the scale one or two more digits. And here I've shown you the ratios of these intervals from word to word to word to word to word. Now, this is what a mathematician would call a mixed radix numbering system. The way we usually use numbers, base 10 numbers, common numbers, is that every digit in a number has a value that's 10 times the value of the previous digit. So the radix, to use a mathematical term, is 10, 10, 10, 10, 10, 10, 10, obviously not mixed. But this is just your motivation to getting into the world of thinking in logarithms. And we do have in common language the phrases 5 figures, 6 figures, 7 figures, referring to these numbers, and of course, we're going up by powers of 10. And what we're referring to by 5 figures is there may be a whole bunch of leading zeros, but we ignore those. What we're interested in is the number of figures from the first or leftmost non-zero digit to the decimal point. In this case, 5 or 6 or 7. And why we don't talk in common language with phrases 4 figures or 8 figures, well, I'm not sure. Now, there's another system we use in science and engineering that involves ratios of powers of 10 up and down a scale, except we use powers of 1,000. And that is the SI unit multipliers, kilo, mega, giga, tera. They're related by fixed powers of 1,000. And similarly, below 1, it's 1,000th. But you can think of this as being an example of a logarithmic system of measurement, but using base 1,000. And it's very useful for science and engineering, but not useful for engineering. Another example of logarithmic coding is based on the fact that human hearing senses sound levels, loudness, if you like, approximately by ratios, not by absolute power of the sound. And this is very much like the Code 100 problem that I described in an earlier class, where vision also really responds to ratios. And because logarithmic numbers are themselves ratios. They're a very natural way to express sound pressure and also light levels. Now, in engineering and even in image engineering, sometimes we use powers of 10, and these, in the case of measuring light, are called density units. So the optical density of a certain amount of light is just the base 10 logarithm. Now, if the object is absorbing light, that would lead to values that are negative. So sometimes we just discount the negative sign in front of that. But these ratios of 10 are really too large to be useful to the craftspeople, like, for example, the cinematographers. And so it's common in photography to use powers of 2. And here I'm starting with 1.0 being the maximum value and then going down from there. So the powers are actually negative. Or I should say the base 2 logarithms are negative because the quantity being presented to the logarithm is less than 1. But we're going down factor of 2, factor of 2, factor of 2, factor of 2. And that, as we all know, is called a photographic stop. Now, there's a very interesting relationship between the base 10 density units and the base 2 stops. And that is that 2 to the power 1 over 3, 2 to the 1/3, is about 1.259. And 10 to the power 1/10 is about 1.260. So those ratios are so close that for all practical photography and imaging engineering purposes, we can consider 3 1/3 stops to be equivalent to a density unit. Or flipping that around, 1/10 of a density unit is 1/3 of a stop. And that 1/3 of a stop ratio turns out to be extremely useful for image engineering. And in fact, if you pick up a camera and look at its shutter speed dial, and I think I do that, you'll notice that it doesn't actually go up by exact powers of 10. So, it doesn't go up by exact powers of 2. If so, it would read 8, 16, 32, 64. Instead, that scale has been adjusted a little bit so that this particular dial goes up to exactly a factor of 1,000. And those are the approximations that are used in photography. So in photography, we don't actually use exactly powers of 2. We approximate that as a stop being 10 to the power 0.3, which is about 1.995 instead of 2. Now, obviously, we all know when taking photographs, it doesn't matter whether you dial up the exposure by a stop or by 1.995 factor. In practical terms, they're both identical. But keep in mind, we tend to express these things in the base 10 equivalents and not exactly in base 2. And if they were exactly in base 2, you would have seen 1024 at the top of that scale. Now, I'd like to give you a sense of how those numbers work over a scale of 1,000 to 1. And the basic principle of logarithms is divide that scale so it doesn't go up by 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, all the way from 1 to 1,000, which would be 1,000 steps, or 999, depending how you count. Instead, what we want to do is go up that scale in ratios, like compound interest, because vision sees basically by ratios. And that's the whole Code 100 Weber fraction 1.01 multiple being the value that really no human observer can see a ratio of luminances less than that. But it's all about ratios, it's not about absolute values. So here we're marching up the scale from 1 to 1,000 using 1/3 of a stop, or 1/10 of a density unit. In fact, in my scale, I'm using exactly 1/10 of a density unit, which is very, very close to 1/3 of a stop. And I'm putting the stops on the left because this is the photography space where they're comfortable talking in stops. And I'm putting the factor of 10 density units on the right because I'm imagining handing the photography over to the lab or handing it to the engineers or giving those light values to a camera where the sensor designers and the camera designers work in base 10 logs instead of base 2 logs. And so you can see that there's 30 steps of a third of a stop, or in other words, 10 stops. And I've taken them up by numbers 1, 2, 4, 8, 16, 32, which are exactly powers of 2, although in the exposure time setting dial a moment ago, they were using 30th and 15th instead of 32 and 16. But then the next one, I'm picking 63, and then 125 instead of the exact 128 power of 2, and so on. Now, I'd like you to think of relating this scale to a grayscale chart that goes from black to white. And this particular chart that you've been seeing, the Macbeth chart, or the color checker, has got grayscale steps. It's got a white, it's got what they call black. But the chips in between are not really sensibly spaced in terms of photography. So for photography, it is the case that when you build a chart out of paint or pigment on paper, you get a reflectance from the white chip only maybe 90%. And the reflectance from the black chip maybe 3 or 4%. So the contrast ratio between white and black here is maybe 25 or 30 to 1. But here the steps aren't divided very well. So let me forward into the next slide that shows you a different grayscale chart, but this one containing levels of gray which are, I can loosely use the word calibrated. The tolerances aren't very tight, but loosely those chips are at 1/10 of a density unit apart, and that's how they're labeled with numbers. Or you could also think of them exactly equivalently being a third of a stop apart. But now I've put them on the chart so that 100 corresponds to the white chip. And you see we don't quite get 100 to 1. We don't quite reach the 1.0 because the darkest chip has got a contrast ratio of only about 50 to 1. And if you look at this chip actually in practice, you find that for that last black chip, they've used a different kind of paint that's quite shiny. So this is comparable to the DSC Labs Cameline chart that I was showing you earlier, where they're using a glossy black because it can achieve a lower black level, having to do with the way things reflect off the surface of the card. So now you can think of this grayscale card representing a scene. And you get to decide how much room you leave above that diffuse white for specular highlights, the things that sparkle, chrome, glass, the glint from someone's eye. And you get to determine whether you need any space below that, because you might find that in some parts of the scene they're in shadow, and the lighting here is done so well that it's difficult for me to find a shadow. But if I place the card in shadow, effectively you find it just slides down that scale. So you might want to take the 25 to 1 contrast ratio of a Macbeth chart as your reference, but imagine the Macbeth chart under a tree and the Macbeth chart out in the open, and those white reflectances might vary by 2 stops, or worst case, maybe 3 stops. So you need some latitude about where you place the reflectances of the scene on the scale available to you in the camera. Now, this would be a 10-bit camera if it ranged from code value 1 to code value 1,000. And it's more typical today to have a 12-bit camera going up to code 4,000, or maybe even a 14-bit camera, but that's another story. Now, I've introduced you to logarithms, and the notion is we go up the scale like compound interest. And curves like that are used in cameras. But it's a characteristic of a logarithm plotted here in blue that logarithms keep on going down toward negative infinity as the quantity you're taking the log of gets smaller and smaller and smaller and smaller. And this is quite distinct from a power function here graphed in red, where the power function of 0 is 0. And then it's just all over. So the range of values you get for really, really low exposures is limited to this range in the power function, graphed in red, but it just never ends in the logarithm. And in fact, if you capped the camera and had then a perfect logarithm function in the camera, it would report minus infinity. So at some point, you got to call it quits. And in any event, the noise characteristics of the camera don't give you useful values down in that region anyway. Now, you've already heard about how HD cameras commonly had to avoid the infinite slope of a power function by putting an arbitrary linear slope limit on the bottom and then stitching the power function into the top. And that's a characteristic of a gamma function for an HD camera. But in logarithmic functions, and you can tell where I'm headed. I'm headed towards Panalog, SI log, RE log, Red log, Sony log, and so on. They're all variations on the same theme of basically modifying the log function so it doesn't crash all the way down to minus infinity when you cap the camera. And the way we modify it, it's a little technical trick. You insert a little additive constant added to the exposure before you take the log. And I'm not going to go over the details of that. That's in the more advanced class, for example, DCT 301. But what I will tell you is that scheme is absolutely common among all the log codes that are used in practice for acquisition of digital cinema. And of course, there's no reason you couldn't use such a camera for acquiring HD, except then in the grading system, you've got to do that compensation from logarithmic to HD coding. And I should just insert here, some people call that log to lin, and that's a really super horrible bad word because linear really is most usefully reserved for linear light or scene referred or radiometric or physical, as opposed to the perceptual coding that both log functions and power functions can do. And you can see from this graph that I've constructed an example of a pure log plotted in blue and a pure power function plotted in red. And they're both comparable over a large range of exposure values. And I've plotted this plot out to 1.5, but in practice, we're likely to want to have diffuse white around 1, white shirt white, paper white, and it reports a certain value in the video scale. But we're usually going to have capture scenarios where some of the things in the scene sparkle, and they're basically collecting light energy somehow and exhibiting mirror-like behavior, shipping you little tiny bright sparkly points into the camera that exceed the pixel value of reference white. So again, reference white is represented by something like the Corley cam white chart, but things sparkle and produce pixel values higher than that. And you have to clip those for graphic arts, because in graphic arts, you have to reproduce white as the white of the paper. But in cinema, you can put white anywhere you want and leave room for things that are brighter than white. Now, you can see from these curves, the log curve tends to compress as you get higher and higher and higher. So if you imagine these camera exposures going 3 stops above diffuse white, the scale going out to 8.0 instead of 1.5, then the log curve here in blue is going to compress those specular highlights much more than a power function curve like the one sketched in red. And so log curves tend to be better behaved for really high intensity highlights and also have better behavior for low lights. So if you're in a situation where you want to be capturing information, and this could either be digital still photography or motion, cinematography, videography, even HD, even HD acquisition, you might be better using a log-ish curve. And I mentioned in an earlier class Sony HyperGamma, which is kind of a compromise to use an HD-like gamma function, but give you a few of the benefits of a log-ish curve by just stretching those blacks a little bit and pushing the speculators down a little bit. But Sony don't give you the inverse of that curve. So it's very troublesome for VFX. Much better to use real log curve at the front end. Panalog, Sony log, ARRI log, SI log, Red log, all of those log curves. They're functionally absolutely comparable. And that's the basic math. You can think of this diagram as giving you the introduction to that. Now that I've explained the log curves, now, finally, we're in a position to give you a really deep, I think really deep, although superficially it looks simple, but a really deep explanation of bit depths used in digital imaging. This slide shows a bunch of different data formats and bit depths used in a bunch of different scenarios, both at the camera, in capture, in VFX, linear light, and in distribution. And you have to think of this diagram as being multiplied by 3. There's 3 of these diagrams, one for each color component, red, green, blue. But they're typically, in fact, always practically, they use exactly the same bit depth in all 3 components. So just one of those components suffices for me to give you this explanation. So we start with the lowest level of quality and we'll work up. And the lowest level of quality would be sRGB 8-bit components, 888 or 24 bits per pixel, being used in consumer video and commodity desktop computer graphics. And here, as you well know, it's perceptually coded. So these are sRGB codes. If you like, you can compare them to the Photoshop example of 128, 128, 128 being halfway up the scale. Now, and that achieves very adequate performance, up to contrast ratios of 1,000 to 1 or so, no particular problem. Now, in order to get into that space from a radiometric camera, and virtually all the cameras we use in image acquisition start by just effectively counting the photons. So the cameras we use have got sensor devices that are intrinsically linear light, but typically in the camera right after the sensor, we've got a curve that goes into perceptual space for use in recording and interfacing. So to match the performance of 8-bit code, nonlinear perceptual space, we need about 10 bits of linear light space in each component. And that performance would be achievable in, say, my iPhone camera. I mean, I don't know the details, but I expect this to be a 10-bit camera. And there are even certain digital cinema cameras that have been 10-bit converters, but that's a story for another day. Now, as we all know, progressing into high-end HD production, even 10 or 15 years ago, the community realized that we really needed more than 8 bits to do the production, partly because we're layering and compositing and mixing and wiping and doing image operations and introducing a few errors. So we need a little bit of latitude for error tolerance or you could say processing tolerance. So we added 2 bits. And the standard for HDSDI in the studio is 10 bits per component. And you could use RGB components or you could use YCBCR components. They're both comparable. Now, if you do 422 subsampling, you squeeze it some more. But in any event, their 10-bit components are common. And in the early stages, I'm referring to 20 years ago, of digitizing film, Kodak decided that 10 bits of optical density measurement of film, so if you like, I introduced this term in the last class, Cineon printing density values, often recorded in DPX files, they're typically 10 bits. Now that scheme was introduced in a system that had 10-bit, 10-bit, 10-bit software. 2 bits of padding made a 32-bit word, highly software friendly. But there's no reason you couldn't also transfer those 10-bit components across HDSDI, but now coded like film instead of coded like HD. In any event, 10 bits per component suffices. And to map either of those into the linear light domain requires, again, about 2 more bits. So 12-bit linear light, and that was implemented by cameras like Sony f950, RED21, the Red One, and the Silicon Imaging camera. Perfectly respectable, but some people wanted more quality than that. And so the state of the art today for digital cinema or even HD acquisition would be a 14-bit converter on each of the 3 channels. And that's characteristic of F35, F65, Alexa, and Epic, just to pick a few examples. Now, 14-bit linear light is equivalent to about 12-bit nonlinear perceptual coding. And 12-bit perceptual coding is what was chosen for digital cinema distribution, as you well know by now, with P3 primaries and a 2.6 gamma. Now, and that's today, and that looks like it's got lots of room for growth in the future. Probably 12 bits can even handle higher dynamic range in emerging technology. Now, where this diagram ends up is collecting all of those ideas into one format, OpenEXR, now it's floating point. And because now you know something about logarithms, you can imagine if you code a number, but you allow the decimal point to float back and forth, you could code a 5-digit number in 5 figures, like 89,253 decimal point. But if you simply moved the decimal point, you could also code the number 8.9273. All you need to know is where you put the decimal point, and that'll take a very small amount of information. Here there's only 5 different positions and 5 digits. Well, that's what's going on in OpenEXR. There's a fraction component and there's an exponent, which is exactly equivalent to the base 2 logarithm, and the exponent simply says where to put the binary point on this large number of bits. Now, in OpenEXR, the large number of bits turns out to be 42 bits per component because there's 32 different places you can put the decimal point, and even if, the binary point, I should say, and even if you put the binary point really close to the bottom of this field, you've still got 10 bits left in the fraction. So it's effectively 32 bits plus 10 bits worth 42-bit number. However, what you do is you scan across all the leading zeros until you come against the first non-zero digit, and then code the next 12 digits in binary, 10 bits, and that's all. So if there's more bits beyond that that are providing additional precision, we throw those away. So in some sense, it's a little tiny bit lossy, but in practical terms, it's beautiful. And this coding, I've color-coded here the physical linear light components to be green and the perceptually coded nonlinear or very, very roughly logarithmic components to be blue. And so I show OpenEXR to have blue 5 bits corresponding to the exponent and green 10 bits corresponding to the linear light fraction. So really, it's the best of both worlds in perceptual and physical encoding. And that explains why it's becoming quite popular, really practical, works well for CPUs, GPUs, and it's obviously the way of, major serious movie productions today. And lots and lots and lots of image work in the future. So I've taken you in the course all the way from just the absolute basics of RGB mixture into some amount of detail about how we represent images in different forms. And I hope that's covered a good broad swath through color technology for digital imaging. And it's been a great pleasure doing this for you. And kudos and compliments to the FX PhD team for doing a great job on the production. See you next time.